And good morning, everybody, and welcome back to Calc 3. Plan for today is I have a quiz for you on Standard 5, and then we are going to continue our discussion of Standard 6, looking more at properties of multivariable functions. I've got my usual office hours on Monday, in the hour before class, and from 2 to 3. And as far as homework goes, only homework coming up is Exam 1 on Monday. As a reminder, that will cover standards 1 through 5. You will be allowed one sheet of notes front and back, so I encourage you to write up some notes that you think might be helpful for you over the weekend. You get to keep it after the exam. I don't care what's written on it, just one sheet front and back. Any questions or comments before we get started for today with the quiz? Why is it always a good idea to try and make friends with an abacus? Because an abacus is always going to be a friend you can count on. Thank you. All right, I'm going to go ahead and pass out the quiz for today. As usual, you'll have about 10 minutes. We'll start with this side of the room this time. Sit up a little bit. Oops, sorry. Let's see. Bless you. Go ahead and take a few seconds to finish up your thoughts. And pass your quizzes forward, please. Pass your quizzes forward, please. Right? Oh, sorry about that. I gave it to you so you could take the quiz twice if you really wanted to. Disappointed that you didn't. Thank you. Alrighty. So, last class we started Standard 6, kind of talked about what a multivariable function is, where we said it's just going to be a function that, let's taper this back a little bit, it's a function that takes in vectors and spits out other vectors, where the input and the output vectors could potentially have different dimensions to them. We said that the domain of the function is just the set of all the things that you can plug into the function, all the inputs. The codomain is the set where all of the outputs live, so basically Rm for some m, corresponding to the dimension of your outputs. And the range, finally, is going to be the set of all the vectors that are actually going to be outputs. So the set of things that you can actually get by plugging something into your function. And I would like to start off by looking at a specific function. Pull it up on the screen here. X of t equals cosine of t, y of t equals sine of t, and z of t equals t. So this is a function that's in parametric coordinates. We're going to write it out as f of t is equal to cosine of t, sine of t, comma t, where t is being forced to be greater than or equal to 0. But Dr. Gerstle, you graphed 0.2 times t, not t. Pretend the z-coordinate is just a t. I multiplied it by 0.2 to make the graph easier to look at. But what we get when we graph out this parametric function in parametric coordinates is going to be sort of this coil-like shape, sort of starting at 1, 0, 0, and then spiraling upwards. Let's knock over my computer. Where the fact that our x-coordinate is cosine of t and our y-coordinate is sine of t tell us we're going to have this circular pattern, corresponding to the fact that as t increases, meaning z-coordinate goes upwards, x and y are kind of going to circle around the z-axis, as cosine and sine tend to do. And what I would like to do is I would like to find the domain, the codomain, and the range of this particular function. What are all the inputs? Where do all the outputs live? And what vectors can we say are going to be outputs to this function? So to start with, let's look at the domain. What exact? Yes, Ellen?
So when you say that a vector is an output of a function,
Correct.
what does that mean? It kind of looks like just points and things.
It's true you could think about it as just, it's true that the outputs look like a set of points. You could think about it as being a set of points or as a set of vectors. Give me just a second.
Are they all vectors like coming from the origin and then ending on
Yeah.
the side?
So one thing you could think about is sort of like at each point kind of associating to it the corresponding position vector coming out of the origin, so to speak, for different values of t. Cool. Let's get rid of this one then. So let's start off by looking at the domain of this function. What are we actually going to be plugging in to this function in order to get our outputs? Are we plugging in vectors in R2, R3? Are we plugging in scalar values? What sorts of values are we actually plugging in order to get an output?
Just scalars, right?
Just scalars. Yeah. All that we're going to be plugging in is values of t. Our inputs are going to be scalar values. So what would you say that our domain is more specifically?
R. Well, greater than 0.
Yeah, the fact that we're being given this extra constraint that t has to be greater than or equal to 0 means that I think our domain here is just going to be the set of all positive or 0, or non-negative, let's say, real numbers. So either the interval from 0 to infinity, or if you prefer, you could write it out using this set builder notation, the set of all values t in R that satisfy the condition t is going to be greater than or equal to 0. So the domain here is actually only consisting of scalar values. Even though our outputs are multidimensional vectors, the inputs themselves are just going to be individual values for t. How about the codomain? In other words, what set, which Rn do all of our outputs live to this function? Huh?
R3.
They're all going to live in R3. We're getting outputs that have 3 dimensions to them. X dimension corresponding to cosine of t, a y dimension corresponding to sine of t, and a z dimension corresponding to just the last coordinate t. So that means our codomain is going to be in R3, where our outputs live. So we have a function that takes in scalars and spits out 3-dimensional vectors, or points if you prefer to think of it that way. Last one is going to be the trickiest, and unfortunately I have to mute the graph here because I'm not given much board space in this room to work with. Let's talk about the range. And this one's going to be pretty tricky. What can we say about vectors that are actually going to be output? They're all going to be vectors in R3, but we're not going to get every vector in R3. Only the ones that correspond to points that kind of live along that spiral. Molly? Okay, they're all that's good. All the points are within one. I would actually say they're exactly 1 unit away from the z-axis. At any fixed value z, at least. Okay, so that's something we should consider. That all of them are 1 unit away from the z-axis, somehow corresponding to the fact that our x and y coordinates correspond to cosine and sine, respectively. Sarah, did you have a hand up?
That was just to say that all of them are going to be vectors.
Yeah, they're all gonna. I would technically not say they're going to be unit vectors, because the z coordinate can be as big as we want it. It can get really, really big. They're all going to be 1 unit away from the z-axis, but that doesn't mean they're going to be 1 unit away from the origin, so to speak. Here, I'll draw like a copy on the board here so that we can kind of look at it. That we have this spiral going up. So I'll make some notes here. All 1 unit from the z-axis. That's helpful to start. What else can we say? Well, you look like you have another thought.
Yeah, they're within one and negative one and
Aha! So we know that our conditions are ultimately going to be saying vectors in R3. And as Emily has noticed, that the x-coordinates and the y-coordinates are always going to be between -1 and 1. Why is that? What makes you so sure they're going to be between -1 and 1? Yeah, since x and y are both or cosine and sine of some value respectively. Since cosine and sine only give you values between -1 and 1, that tells us that the values that the x and y coordinates of vectors in the range are also going to have to be between -1 and 1. So right now, if we took all the vectors whose x and y coordinates are from -1 to 1, we would be essentially getting like a big square that extends upwards and downwards forever. It's basically the square of vectors in the plane between where x and y are between -1 and 1, but then going up and going down unless we restrict our z somehow. What else can we say about the vectors in the range? I'll tell you what, why don't you all think about this for a minute, and I encourage you to talk to the people sitting around you. You're certainly welcome to talk to your neighbors about this, and see if you can come up with any more restrictions that will categorize the vectors or points that are going to be outputs to this function all have to be exactly these vectors. Using the fact that the z coordinate is t, the x coordinate is cosine of that t, and the y coordinate is sine of that t. What do you mean by the distance based on z?
So, like, whatever z value you have,
I mean, you could certainly say, like, something like this. Do you mean like a function that measures distance from the z-axis? From the origin? Sure.
Because since it's always one away from would that be helpful for this?
Could be. You could figure a way to kind of write that into an equation somehow.
I don't know.
Exactly where they go.
Okay, I'll seem to have quieted down. What thoughts did y'all have? Yeah, Laura?
I don't know if it's correct, but I was thinking maybe we could do cosine t plus sine t equals plus or minus 1.
There is a relationship that cosine and sine have to satisfy. I don't think it's just cosine of t by itself plus sine of t equals something, but I think you're onto something. There is a sort of a can't even say the word, trigonometric relationship that cosine and sine have to satisfy with each other. Anybody remember what that is? Involving
Cosine squared plus sine squared equals 1.
Yeah, we know that cosine squared t plus sine squared t has to be equal to 1, no matter what you plug in for t. So how can we make that a relationship about x, y, and z here? If x is cosine of t and y is sine of t,
Well, cosine z squared plus sine z squared equals 1. Z is t.
true, that's something we don't necessarily need to write as a restriction, though, because that's always going to be the case, no matter what. But instead of making that instead of saying that as an equation about z, how can we write that as some equation involving x and y? No? Yeah, you could write that as x squared plus y squared is equal to 1. Because if x is cosine of t and y is sine of t, then x squared plus y squared should just be cosine squared plus sine squared, which would in fact give us 1. So that tells us a nice condition that whatever x and y are, x squared plus y squared is equal to 1. Which, if we restrict ourselves in that way, what we're going to get is no longer an infinite rectangle. It's going to be a cylinder that goes up and down forever, kind of centered at the z-axis. We're getting closer, but we're still not quite there. We have an infinite cylinder instead of an infinite spiral right now, based on these conditions. Tim?
Well, because t is greater than or equal to 0, z has to be positive.
Aha! That's a nice condition we can have. I'm going to erase these top two. X and y are between -1 and 1 because x squared plus y squared equals 1 automatically implies that. As Tim pointed out, the condition that t has to be greater than or equal to 0. Well, if z is equal to t, that should certainly tell us z is going to be positive. So now our cylinder only goes up forever. It doesn't go down forever. It stops at the z. It stops at the plane z equals 0. We need something a little bit more subtle. Because right now, I think this x squared plus y squared equals 1 formula is certainly true. Z greater than or equal to 0 is certainly true. Right now, what might be helpful is to find some sort of relationship between x and y and z. Because right now, we know nothing about the relationship between these two variables and z that I think we should be able to maybe see if we look at the function again. Oop.
Since z is equal to t, can you just say then that x is equal to cosine of z and y is equal to sine of z?
Ooh, I like that. So in other words, z is equal to t, x is equal to cosine of t. By substitution then, whatever cosine of t is, which is x, should be equal to cosine of z. Yeah, so I think that's a great way to describe it. You can say that x is equal to cosine of z. And can you remind me what you said about y?
Oh, that y was equal to sine of z.
Yeah, by the same logic. If y is sine of t and t is z, then y should be equal to sine of z. And I think if we add those restrictions, that is just going to leave us with this spiral right here. If x and y are both sine or cosine and sine of z respectively, we actually don't need the x squared plus y squared equals 1 condition. That's something that's implied by having x and y be cosine and sine of z respectively. So I think this is going to be our final answer for the range. It's going to be the set of all vectors, x, y, z, and R3, where x is going to be equal to cosine of z, y is going to be equal to sine of z, and z has to be greater than or equal to 0. I like that, Tim. I think we still need to have that just to make sure the spiral doesn't only goes up forever instead of down forever as well. Dr. Gerstle, why did you subject us to this? I wanted you to see an example of how finding range can be kind of tricky. In that you sometimes can see a lot of relationships, like it's certainly true that x has to be between -1 and 1, y has to be between -1 and 1, but sometimes you can add restrictions to your vectors in the range, and it's not enough. You've restricted your range somewhat. What you say is the range somewhat, but the actual range is still smaller. It doesn't include as many vectors. And so going through and actually having to compute this sort, why does I have range of t? That should be enough. Going through and actually finding the range means restricting yourself all the way that's necessary so that you only get the vectors or points that that's actually being graphed out here. Yeah, Brenna?
This is just a question, but for for the domain, do we have that t is just an r because it's a scalar value?
Yeah, because t, here if we're taking cosine and sine of t, we don't have a way to take cosine and sine of a 2 or 3-dimensional vector. So that, I'll say something like that, or by saying t is greater than or equal to 0, those sorts of things kind of imply that t is going to be a scalar value. And in general, throughout this class, if you ever see me write t on the board, t is pretty much always going to refer to some scalar value. Yeah, that's a good question. How did we know that? No?
What are certain conditions or like criteria that tell us when we're done with
Basically the condition, how do you know you're done? Basically, you have to encapsulate every single piece of information that you can kind of squeeze out of what the function says. So basically here, we know we needed z greater than or equal to 0 because of this condition. But once we've written z greater than or equal to 0, we don't need this anymore. That's kind of, this part's done. And if you look at what's left, if z is t, x is cosine of t, y is sine of t, by saying x is cosine of z and y is sine of z, that's telling us the exact same information as this formula does right here. So how do we know we're done? Because there's literally nothing else I can squeeze out of here. I mean, you could say something like x squared plus y squared equals 1, or x is between -1 and 1, and it wouldn't be incorrect to do so. But that's still something, but that's information you could have already gotten from just looking at the restrictions that are already there. Like this automatically implies x is between -1 and 1, ditto for y. X squared plus y squared equals 1 you could get from pooling these two things together. So we kind of know we're done because there's nothing else that we can add without being redundant. Good question though, because it's not always because depending on the function, it's not always obvious. Tell you what, I'm going to give you all one more to look at, and I'm going to let you all think about this one in small groups again. Let's look at the function f of xyz equals 1 over x minus 5, 1 over y minus 5, z cubed. I'm going to give you all a couple minutes here, and I'm going to challenge you to see if you can find the domain, the codomain, and the range of this function. And if you want, I drew a little hint on the board. Here's a graph of what y equals 1 over x minus 5 looks like. Use that if you, that'd be helpful in, say, finding the range.
So yeah, so x minus
Well, like for this first one, the denominator will always be bigger. Yeah. Okay, so this can be It is 5. I don't know. Um,
Range is always trickier than domain, in my opinion.
right. Well, if you're looking at this as a graph,
Give it another 30 seconds or so, and then we'll come together as a class. So let's talk about the domain. What are the vectors that we're allowed to plug into this function? Yeah, all real numbers except for 5. So you're plugging in single numbers into F. I think you're onto something. We certainly don't want something to be equal to 5. But I don't think we can say our domain is just made up of scalar values. Because it looks to me like we're going to have to plug in vectors. Yeah, I think we need vectors x, y, z in R3 to start off, because we're plugging in 3-dimensional things here. And what do you not want to be equal to 5? X and y not equal to 5? Why don't you want x and y to be 5?
Because it would be 1 over 0, and that would be.
Yeah, if we tried to plug in x is 5 or y equals 5, we would divide by 0, and you should never divide by 0. I agree. Did anybody else have any other restrictions on vectors in the domain? Me neither. I think this looks good. Z, doesn't matter what z is, because no matter what z is, you can always cube it and get something that makes sense. How about the codomain? Where do all the output vectors live? Okay.
R3.
Yeah, R3, because our output vectors all have three dimensions to them. Sort of an x component, a y component, and a z component to them. So domain, all vectors in R3 except ones whose x or y coordinates are 5. Codomain, all of R3. What can we say about vectors in the range? Since our codomain is R3, we know we have to be looking at vectors x, y, z in R3 that do something. But what can we say about our output vectors, if anything? Okay?
So I don't know quite how to restrict the range yet, but I did notice, so in the first problem we did a minute ago, you could define everything by c, because c was just equal to t, and we only putting in one number, but like, we're putting in 3 numbers, it's 3 values, and getting out another 3 values, so I don't think you can really define them by each other. Does that make a difference?
Yeah, I think that's an interesting observation. With the last problem, we ended up with a function that did something like f of t equals, I don't know, 1 over t minus 5, 1 over t minus 5, t cubed. And then we could sort of make comparisons between how the x, y, and z coordinates behave with respect to each other because they were all in terms of the same variable t. But you're right that that's not going on here, where the x component, the y component, and the z component of our outputs are all with respect to different variables. So I think I agree that we're not going to be able to make restrictions this time that's just based on saying, oh, the x coordinate has to be cosine of the y coordinate or anything. I think we just have to make individual statements about the first, second, and third coordinate of our outputs without relating them to each other in this case. Are there any restrictions we can make? Bob?
X can't equal 0 and Y can't equal 0.
X and y can't equal 0. Why can't x equal 0?
There's no way to divide 1 by something to get a 0.
Yeah, if you look at 1 over x minus 5, you can get any real number you want as an output to 1 over x minus 5 here, except 0. No matter what you plug in for x, this expression is never going to be equal to 0. So I like that. I think that's a good restriction to have, that our x coordinate can't possibly be 0. And what did you say about y?
The same thing. Instead of the same.
Yeah. But they're pretty similar to each other. The 1 over y minus 5, no matter what we plug in for y, we're never going to get 0 in this coordinate. So I think we can also say that that the second coordinate, the y coordinate of our output vectors also is not allowed to be 0.
If x number can equal 0 and y can never equal 0, would the magnitude of the vector not be able to ever be 0 as well?
Yes, because the only vector in R3 with a magnitude of 0 is just 0, 0, 0. And just with either one of these restrictions alone, we're excluding 0, 0, 0 from the range. So every vector in the range will have a strictly positive magnitude. I don't think we necessarily need to add that as an extra condition. That would be something that's a little bit redundant to add, given these two. But it certainly is something that's true.
Is that the only restriction you need? Plugging x, y, and z in independently, so I feel like you could get any other value for the thing except for x equals 0 or y equals 0.
Yeah, the nice thing about having the x, y, and z coordinates all depend on variables that are independent of each other, like x outputs only depend on x inputs, y outputs only depend on y inputs, z outputs only depend on z inputs. The nice thing is we don't have any sort of relationship between the individual coordinates in the output vectors, unlike what we did with the parametric example of the spiral. Are there any conditions, though, on the third coordinate? I agree x and y can't be 0 in our output vectors. Can our third coordinate be anything? Dan, I see you nodding your head.
I mean, yeah, I would think that it could be anything, because it could be positive or negative, because it's a cubic function.
Yeah, I would agree. Z cubed is no. We can always plug in. We can get any output we want by just plugging something into the cube function, since the cube function has a range of all real numbers. How would it be any different if I replace z cubed here with z squared? Or?
Well, if it's z squared, it would only be positive.
Positive or 0, so then we'd have to have a restriction saying something like z is greater than or equal to 0. But yeah, the fact that we have a cubic function here, that makes everything okay. We don't have to worry about putting an extra condition on our z coordinate, and I think this is something that's totally fine as the range.
Alpha's function, or the other alpha.
We're going to be talking about that later in the packet. I would say it's impossible to graph this function because we have a three-dimensional input, we have a three-dimensional output. That would be trying to graph a six-dimensional function. Do you want to try and draw something in 6 dimensions? Me neither. would say this is not one that you could. The last function had sort of like was okay because we were only plugging in a single value for t and we're getting a three-dimensional output. So that was something that we could sort of visualize by, oh, different values of t are giving us these different points in the XYZ plane. But with three-dimensional inputs, and three-dimensional outputs, there's just too many variables for us to really be able to visualize. So it's a good question, one worth asking. Like we graphed the last one, why can't we graph this one? There's just too much going on, I think, with this function. This is actually something that we could graph. F of t is 1 over t minus 5, 1 over t minus 5t cubed. That would be something we could graph, theoretically, but not this one.
Would the two be similar?
Algebraically, they behave in somewhat similar ways. I don't think visually you could really make. Well, that's a good question for after class. I was gonna say I don't want to get into projection mappings and it's the same thing. You're just losing some information by restricting yourself so that every variable has to be the same. Yes, there are definitely similarities that can be drawn here, but they're not very obvious or particularly easy to discuss. Other questions or comments? All right. So next up, that's kind of it for domain, range, and codomain for now. I think when you have these sorts of functions with lots and lots of variables, like three-dimensional inputs, three-dimensional outputs, typically we can't really graph a lot of these. But by looking at domain and range, what can we plug in, what can we get out, that's still telling you, I think, some good information about how the function still behaves. Meaning it's still behaving. Don't beep at me, camera. It's behaving in a way that you can get these sorts of outputs. It's behaving in a way that you can get these sorts of inputs. It's behaving in a way where here's where the outputs live. So finding domain, range, and codomain, it's not as good as graphing your function, but depending on how complex your function is, it's as close to an approximation of graphing as you're going to get. So next up, I want to talk about how to take a function that's a multivariable function and break it up into smaller pieces. And to do so, we're going to need to talk about component functions. So in general, you can say that given any function, f, that's taking in values in Rn and spitting out vectors in Rm. So it takes in n-dimensional vectors, it spits out m-dimensional vectors as outputs. We can break f up into smaller functions. And these smaller functions, we're going to call its component function. Where the idea is that if you have, let's say, an n-dimensional input, so if you have an f of x1, x2, up through xn, in this case we have a three-dimensional input, since our input vectors have 3 coordinates to them, we can always take our vectors and split them up so that our outputs have m dimensions to them, and each of the kind of functions corresponding to the m dimensions of the output are going to be our component functions. f1 of x1 through xn, f2 of x1 through xn, all the way up to f sub m of x1 through xn. And let's take a look and see if we could tell what does this mean. Like, what does it mean to take this and break it up into component functions? Well, the idea is that if you have a function that behaves something like, let's say, f of x comma y is equal to 3x plus 2y, 2x minus cosine of y, and e to the 2x plus 1. So we're spitting in vectors that have 2 dimensions as inputs, and we're spitting out vectors that have 3 dimensions as outputs to this function. what we can do is we can look at each of the individual coordinates of the output vector, and each of those is going to be a separate component function of f. So in this case, we could say that our first component is just what we get looking at the first coordinate of our outputs. We'll get f1 of x comma y is equal to 3x plus 2y. Our first component function corresponding to the fact that the first coordinate of our output vectors is just going to be given by 3x plus 2y, where x and y are both going to be values coming from the input vector's coordinates. So if our first component vector corresponds to our first component, 3x plus 2y, what would our second component vector be? Or second component function be, excuse me.
Yeah, 2x minus cosine y.
2x minus cosine of y. And our third? E to the 2x plus 1. And here are the three component functions of our original f of xy. Our original function had inputs in R2 and outputs in R3. The component functions, however, we can say that the domain of all of these is going to be all of R2. Each of the component functions are still having two-dimensional inputs. What can we say about the codomain of all these?
I have a question about the domain. With the last component one not having a y, is that?
I'll get to that in just a second. I figured someone was going to ask about that. But once I answer this, I'll get into what's up with that last one. So all of them have a domain of R2, the same domain as the original function f. But what can we say about the codomain of all three of these functions? Meaning, where in which Rn do all of the outputs live? Yeah?
Just R, because it's going to be a scalar value.
Just R, because all of our outputs are scalar values. 3x plus 2y, well, if x and y are scalar values, 3x plus 2y is still going to be a scalar. 2x minus cosine of y, that's a scalar. E to the 2x plus 1, that's a scalar. Anytime you take a component function of any function at all, it's always going to have a codomain of R. And so we've taken our original function, which gave outputs in R3, and we split it up into three separate functions, all of which have outputs or codomain that's just R1, just scalar valued outputs. And so that's one nice thing about component functions is it lets you take a function with a multi-dimensional output and splits it up into smaller functions that all have scalar valued outputs. Now, Jacob, I think you were asking an interesting question earlier about, but F3, Dr. Gerstel, it doesn't have any y's in it. Why does F3 of xy's only have x's? It's because you don't necessarily need to have all of your variables show up in the final expression at the end. We would just say this bottom function is constant with respect to y, meaning it doesn't, the y coordinate of your input doesn't affect the output, only the x does. It would be sort of like if this is a Calc 1 class looking at the function f of x equals 2. 1, 2. Just a flat y equals 2 function. Does our output depend on x? Not really. It doesn't matter what you input, your output's the same. But it's still a function of x. we would still say that this is a function with a one-dimensional input and a one-dimensional output. And the same is true for this third component function here, f3, namely that even though only one of the two input coordinates is actually showing up, or actually matters in determining sort of what the output is to this third component function, it's all of these component functions are still going to be functions with R2 as an input. And I would just say this is constant with respect to y. There is some way in that you could say this behaves very similarly to the function f of x equals e to the 2x plus 1, but they're not exactly the same function because one's going to be a three-dimensional function and one's going to be a two-dimensional function. Does that sort of get to your question? Well, all three of these. The way it's written, f of 3 of xy equals e to the 2x plus 1. And the reason why I say it's a three-dimensional function is because if we were to graph it, it would be a 3D graph, where we would have x and y inputs, and the output would be our z coordinate of the points we would graph. It would very distressing. That's going to be what we're talking about next. That's a little bit of sloppy notation, but I say a three-dimensional function. That's me speaking a little carelessly, I guess, there. But what that means is if we were to graph any one of these, they would be three-dimensional. The graphs would be in 3D. Whereas if I were to just graph f of x equals e to the 2x plus 1 as a calc 1 function, that would be a 2D graph. We would just graph that in the plane. Let's do one more example where we're given a function and we need to find the component functions. And the function I want to look at is the same one that was on the front page of the packet. F of a vector x is equal to x divided by the magnitude of x, or 1 over magnitude of x times the vector x, where x is going to be any vector in R2. Dr. Gerstle, it says R3 in the I want to do R2. I changed my mind after printing out the packet. So this is going to be a function that takes in vectors in R2 and spits out vectors in R2. I would like to find how can we write this function how can we find the two different component functions of this function f? Because we should have a different component function for each coordinate of our output vectors. And since our output vectors are in R2, we should be able to have two separate component functions. There's a problem here, though. Our function, as written, isn't in the form where we can see, oh, here's the first coordinate of the output, here's the second coordinate of the output. So what could we do if we wanted to fix that? If we wanted to say, rewrite the function so that we could see the individual components of the output vectors, how could we rewrite this expression 1 over magnitude of x times vector x?
Replace the vector x with x, y.
Sure. So instead of writing f of vector x equals stuff involving vector x, we could just as easily say f of x comma y, where now x and y are both scalars, is equal to 1 over the magnitude of x comma y times the vector x comma y. What's another way that we could write out the magnitude of x comma y? What was sort of our formula in other words, for finding magnitude. Yeah, favorite? Yeah, just square root of x squared plus y squared, using the Pythagorean theorem. And now, if we can use our knowledge of scalar multiplication to write this as a single vector, we're taking the scalar 1 over square root of x squared plus y squared and multiplying by the vector xy. If we combine these, we'll get x divided by square root of x squared plus y squared, comma y divided by square root of x squared plus y squared. And now I think we can actually write out what our component functions are. So what's going to be our first component function here? A component function corresponding to the first coordinate, in other words, of our outputs. Huh?
X divided by square root.
X over square root of x squared plus y squared. I like it, because that's the x coordinate of our output vectors. And then our second component is just going to be y over square root of x squared plus y squared. Both are going to be functions that go from R2, the same dimension as f for our input vectors. Both f and our two component vectors, or component functions, I keep saying component vectors when I mean functions. Both the original function and our component functions have inputs in R2, but while our original function had outputs in R2 as well, our component functions are going to have scalar valued outputs. Because no matter what your x and y are, x over square root of x squared plus y squared is just going to be some scalar, and ditto for f2. This is going to be useful to us in that while we can't really graph this function, there's too many components to it, we're going to be able to talk about how we could graph f1 and f2. And so while we don't have a graph for our entire function as a whole, we can graph the component functions in this case, which we will be doing on Wednesday. So as a reminder, on Wednesday we'll finish off Standard 6, talk about how you actually graph functions from R2 to R. On Monday, though, we will have our exam, and so I encourage you all to study over the weekend, make your sheet of notes. Feel free to email me or reach out to me if you have any sort of questions going into the exam. And I'll leave it up, and I'll update everyone's totals on Blackboard over the weekend and email you when I do, so that you'll know exactly which standards you still need to test over for Monday's exam. Have a good weekend, everybody.